Hysteresis. When a ferromagnetic material is taken through one cycle of magnetization, the magnetic induction B or the intensity of magnetization I lags behind the external magnetic field H. So this shows the hysteresis law. Let us consider a ferromagnetic material. When a magnetic field H is applied in the positive x direction, the magnetic induction also increases and it reaches a saturation at this point. So after saturation is reached, if we still increase the magnetic field, the magnetic induction will not increase because it has already reached its maximum limit. Now, when we try to decrease the magnetic field, the magnetic induction also decreases, but when the magnetic field is coming to zero, the magnetic induction is not coming to zero. Instead, it has got this much amount of residual magnetic induction even when the field is reduced to zero. This residual magnetic induction is what is called a remanence. Otherwise, it is known as retentivity. So, in order to bring this residual magnetic induction to zero, we are going to apply a field in the reverse direction. So, when a magnetic field is applied in the reverse direction, at this point, the magnetic induction, that is the residual magnetic induction, comes to zero. So this portion is what is called coercivity or coercive force. It is the amount of magnetic field that is applied in the reverse direction in order to bring this residual magnetic induction to zero. Now, if we increase the magnetic field in the reverse direction, the magnetic induction takes this shape, and when we decrease the magnetic field, the magnetic induction follows this curve and we are able to obtain this hysteresis loop when the ferromagnetic material is taken through one cycle of magnetization. Thus, when a ferromagnetic material is taken through one cycle of magnetization, there is a loss of energy in the form of heat, and this loss is what is called hysteresis loss. So, retentivity is nothing but residual magnetism or residual magnetic induction. That is, even when the applied field is reduced to zero, the magnetic induction is not coming to zero. So, that is what is called retentivity. Then, coercivity. Coercivity is otherwise known as coercive force. So, when the magnetic field is applied in the reverse direction, the magnetic induction is coming to zero. So the amount of magnetic field applied in the reverse direction in order to bring the magnetic induction to zero is what is called coercivity. So based upon the hysteresis loop or based upon the magnetization behavior, we have two types of materials: soft magnetic materials, hard magnetic materials. So before that, there is a term called energy product. It is the product of retentivity and coercivity. So see the figure. In the figure, 0.13 represents retentivity. The 0.14 represents coercivity. So energy product is the product of retentivity and coercivity. It represents the total energy stored inside the specimen. Then, as I told you, based upon the magnetization behavior or based upon the hysteresis loop, we have two types of magnetic materials: soft magnetic materials, hard magnetic materials. Soft magnetic materials are easy to magnetize and they are easy to demagnetize. That is, they are easily magnetized and also they do not retain their magnetism. That is what is called soft magnetic materials. So if we see the diagram, the hysteresis loop area is very small, which means it is able to magnetize easily and it is able to demagnetize easily. So that is what is called soft magnetic materials. Hard magnetic materials, they retain their magnetism and are difficult to demagnetize. So if we see the hysteresis loop area, we are seeing that it takes there is a large retentivity and also there is a large coercivity. So this type of material is what is called hard magnetic materials. That is, they will retain their magnetism and also it will be very difficult to demagnetize them. Let us see the differences between soft magnetic material and hard magnetic material. So first one, as we saw, they can be easily magnetized and demagnetized. But if we take hard magnetic materials, they are hard to magnetize. Also, they will retain their magnetism longer. Here, soft magnetic materials have high permeability. Hard magnetic materials have low permeability. Magnetic energy stored is low, but magnetic energy stored here is high. Low hysteresis loss, as we saw, the loop area, hysteresis loop area is small in the case of soft magnetic materials. Also, retentivity, coercivity is small. But if we consider hard magnetic materials, there is a larger hysteresis loop area. So, high hysteresis loss, also retentivity and coercivity are high. Then eddy current loss is small in the case of soft magnetic materials. Eddy current loss is high in the case of hard magnetic materials. Here domain walls are easy to move. That is why they are able to easily magnetize and demagnetize. But here domain walls are hard to move. So that is why it is difficult to demagnetize them. Examples are iron, nickel, silver, steels and ferrites. Here examples tungsten steel, cobalt steel, alnico, cuneife, etc. Soft magnetic materials are used as temporary magnets because they are easily magnetized and they do not retain their magnetism. They are employed as temporary magnets and they are used in electric motors, generators, relays, transformers, telephone receivers, radar and sonar equipments. In the case of hard magnetic materials, they are hard to magnetize and also they will retain their magnetism longer. So they are used as permanent magnets and they find application in loudspeakers, electrical measuring instruments.